Must be a bad card. Okay, so consistent systems have at least one solution. Okay, there are instances where you have more than one, and I'll show you those in a little bit. 2, inconsistent systems do not have any solutions. And 3, dependent solutions have infinite solutions. Okay, so those are the 3 types of systems. Okay, so now if you were to look at them as far as graphs, kind of make our XY axis here. Doesn't have to be all that perfect, so we don't need the graphing paper. Okay, separate it, separate that one. Make that our X and Y. They take that. Yes. Oh, sure. There you go. And draw our X and Y axis for that one. Bless you. Okay, so now we're going to look at the graph of an consistent system. Okay, so let's say if you have one graph and you graph it, and that's what you get. You get a second equation and you graph it, and that's what you get. Wherever they intersect, that's your solution. So we know we have at least one solution. Okay, and you have 2 different equations, so they're called independent equations. Or just different. Equations are different. Okay. Now what if we have an inconsistent system? Okay. The only way you can have 2 lines on the same graph and they never, ever, ever intersect is if they're both parallel. Okay. So if their slopes are exactly the same, then you know they will never, ever, ever cross each other. So you know for an inconsistent system, they're parallel. And even though their slopes are the same, they are 2 different equations. Oh, forgot to underline that part. Okay, so they are independent equations, just with the same slope. Okay, so you have no solution. And here you have at least one solution. Okay. Let's say with this one, with your dependent, let's say you graph the first one and you end up with that. But let's say somehow or another you graph the second one and you end up with the exact same points. So the second one is just right on top of the first one. Okay. Now that's how you know you have a dependent system. Okay. Now here where you have equations are different, the equations are identical here. It's just little things kind of make them look different. Okay. And if you remember, the definition of a consistent system is that they have to have at least one solution. If you have an infinite number of solutions, you have at least one. So a dependent system is also a consistent system. At least one solution. And actually here you have infinite. Okay, so those are the three types of systems. Okay, and we're going to actually take a look at all three types by substitution. So like I said, it's a lot easier than solving by graphing. Everyone's done writing. Okay, so let's say, for example, let's say we want to solve the system by substitution. Okay, so let's say if we have 2x plus y equals 10. We have x equals y plus 2. Okay. Now here we can see the second equation is x equals y plus 2. And just to clear it up, we'll call this equation 1 and this one equation 2. Okay, so since equation 2 is already solved for x, because you have x equals and the x is by itself. Okay, we can just get that x and replace this one up here. Replace x with y plus 2 in equation 1. Okay, so that means if we have 2x plus y equals 10, since x is equal to y plus 2, that gives us 2 times y plus 2 plus y equals 10. So instead of having an x and y in there, we have just the y variable, so we can solve for y. Okay, so if we go ahead and distribute that 2, it gives us 2y plus 2 times 2, which is 4, plus y equals 10. And we can go ahead and combine those two. So 2y plus 1y is 3y. So we have 3y plus 4 equals 10. And we can go ahead and subtract 4 from both sides. Well, those two cancel out. So that's 3y equals 10 minus 4, which is 6. So if we divide both sides by 3, we end up with y equals 2. Okay, so we were able to get that one. So we have y equals 2 using the first equation. So if we plug y equals 2 into the second equation, we'll have our x value. Okay, so we plug that into equation 2. Okay, so since our second equation is x equals y plus 2, that just becomes x equals 2 plus 2, or x equals 4. Okay. So we know that the solution is 4, 2. Okay, so you didn't have to worry about graphing both of them. You just get one, plug it into the other, and then solve for your variables. Bring that up a little bit. All right, any questions on that one? Oh, sure. Yes.
So are there going to be equations where it's not already set to like x equals something and we got to change it before we can do this?
Yep, actually we do have an example like that one. Yeah. Okay. Oh, I thought you had a question. Oh. All right. Okay, so let's say, for example, if we have say we wanted to solve by substitution. Say 5x minus y equals -2. And y equals 3x. And we call that equation 1, and we call this equation 2. All right, so this one, we already know we have the y equals 3x. The y is by itself. So since y equals 3x, replace y with 3x in equation 1. Okay, so that means our 5x minus y equals -2. That's going to become 5x minus 3x equals -2. So 5x minus 3x is just 2x equals -2. Divide both sides by 2. We have x equals -1. Okay, so we have x equals -1. Once you solve for one of them, just plug that one in. Okay, so that means, kind of separate that. Y equals 3x just becomes y equals 3 times -1. Okay, so y equals -3. Okay, so your solution is just -1, 3. Bring that up a little bit. Okay, any questions on that one? Oh, -3. Thank you.
Is it ever going to give us a problem where they're not giving you any known value for what variable? Is that what he was asking too?
Yep, and that's the next
Okay.
example. I'm going to do that one.
Okay.
Yeah.
Because I was like, he said there was one, but then this one's all for what?
Yep, so I'm going to do one more, actually the
I see.
last
Okay,
example.
I gotcha.
Alright, so say for our next example, if you wanted to solve the system by substitution, okay, so let's say you have x plus 2y equals 7, and you have 2x plus 2y equals 13. Yep, so this is one of those where they don't have an isolated value. So really all you do, you pick the one that's easiest to isolate a variable, and you just isolate it. Okay. There is no isolated variable, so we make one. And really you can do it for any variable you want to. I just always pick the one that's the easiest, which in this case will be x plus 2y equals 7. So x plus 2y equals 7. If we subtract 2y from both sides, we end up with x equals 7 minus 2y. Okay, so since we know x is equal to 7 minus 2y, this is equation 1, and this is equation 2. So we plug this into equation 2. Okay, kind of separate that a little bit. So that means our 2x plus 2y equals 13. since x is equal to 7 minus 2y, that's 2 times 7 minus 2y plus 2y equals 13. So all we did was replace x with 7 minus 2y. And then from there, we just solve for y. Okay, so we go ahead and distribute that 2. 2 times 7 is 14, minus 4y plus 2y equals 13. Okay. So we can go ahead and combine these two. So that gives us 14. Negative 4 plus 2 is negative 2, so negative 2y equals 13. So we go ahead and subtract 14 from both sides. Those two disappear. It gives us negative 2y equals negative 1. Divide both sides by negative 2. So we have y equals 1/2. Okay. So since we know y is equal to 1/2, we can just plug that into either one of our equations. Plug into plug it into equation 1 since it's a little bit easier than equation 2. Okay, so x plus 2y, oh, sorry about that, 2y equals 7. Since y is equal to 1/2, x plus 2 times 1/2 equals 7, where our 2's cancel each other out. So we end up with x plus 1 equals 7. We subtract 1 from both sides. We end up with x equals 6. Bless you. All right. So any questions on that one? Okay. Now, if you do have situations where if all of your variables disappear after you plug it in and you're left with a true statement like 3 equals 3 or 4 equals 4, that's how you know you have a dependent system.
Because they're right on top.
Yep, they're right on top of each other. But if you have one where if you go through all of this and the variables disappear and you're left with something like 0 equals 8 or something that's false, that's when you know you have an inconsistent system. So you don't have any solutions at all.
Okay, so once you find the pair, that's when you determine if it's one of those solutions or one of those systems.
Yep, because this one's consistent because it has a solution. So you know this one's consistent. So your solution is just 6 1/2.
All the ones we did so far.
Yep, all the ones that had solutions.
But it's only if they have both the equations that are true.
Yep, so if you go through these steps,
True, it's the first one.
yep, so let's say here if we plugged in 7 minus 2y. If all the x and y variables disappeared and you're just left with numbers that are equal, then you know that, okay, it's a dependent solution. All right, yeah, have a good one. You too. All right, have a good one now.
Another major I'm thinking about.